In this video, we are going to be looking at how we determine the shapes of covalent molecules. Now, in order to do this, we need to have a look at this theory over here, and this is called the electron pair repulsion theory, and this is what we use to determine the shape. Now, whenever you're doing this sort of question, the first thing that you should do is draw the dot and cross diagram of that covalent molecule, because if you don't do that, you are very likely to go wrong with the shape. And what you should do is focus on the central atom. So in this case, the central atom is carbon. So we're going to look at the electrons on that carbon. For example, in ammonia, the central atom is nitrogen. For carbon dioxide, it's carbon, and so on. The next thing that you need to know is that given that we are looking at the electrons on the carbon over here, electrons are going to repel each other. Okay, they're both negatively charged, so they are going to repel each other. And as we look at our diagram here, and pretty much all dot and cross diagrams, everything is going to be in pairs. So over here, this pair of electrons is being shared between the hydrogen and the carbon. We've got another electron pair here, another one here, and another one here. So everything is to do with the electron pairs in these covalent molecules. These electron pairs over here, because they are being shared between two atoms, we call them bond pairs. If you have an electron pair that's not being shared between two atoms, it's just on one atom, we call that a lone pair. And bond pairs and lone pairs, any electron pair is going to repel another electron pair. So this electron pair over here is repelling that electron pair, and they are all repelling each other. Okay, so all four of those electron pairs are repelling each other. And that means they want to be as far away from each other as possible. Another thing to note, and this is quite an important point, is that lone pairs repel more than bond pairs. In this one, we don't have any lone pairs, but we are going to have a look at examples that do, and we're going to see what effect that has on the structure. Okay, so we're now going to run through examples of shapes. The first one I'm going to go through is methane, so that's the one that we just had on the board, but I'm going to draw out the dot and cross diagram again. So central carbon had 4 electrons, and by the end it will have 8, and hydrogen had 1 electron. By the end, each hydrogen will have 2 electrons. Okay, so that's the dot and cross structure for methane for our CH4. Now, the first thing you should do is identify the central atom. So in this case, it is the carbon. And then you need to identify how many bond pairs and lone pairs it has. So over here, so remember you're looking at pairs. This one over here, because it's being shared between two atoms, this is a bond pair. And as you can see, there are 4 bond pairs on this carbon. Okay, so there are 4 bond pairs. I'm just going to write that over here. So this has 4 bond pairs. I'm just going to write BP for bond pairs. And it has 0 lone pairs. So I'm going to write LP for lone pairs. Okay, so it's 4 bond pairs and 0 lone pairs. Now, as we said, these electron pairs, whether it's a bond pair or a lone pair, they are going to repel each other. So all 4 of these bond pairs want to be as far away from each other as possible. And remember, this is in 3D, so it does have 3 dimensions to be far from each other. So I've just got a molecular structure for methane. And as you can see, all of these bond pairs, so imagine that the bond pairs are these actual bonds over here, they are as far away from each other as possible. So this is the shape that methane adopts because it has 4 bond pairs and 0 lone pairs around the central atom. And this shape is what we call a tetrahedral shape. So it adopts a tetrahedral shape. Okay, so anytime you have 4 bond pairs and 0 lone pairs around the central atom, it will adopt a tetrahedral shape. We also need to be comfortable in drawing these shapes in 3D. So essentially we are going to be drawing this in 3D. So our central atom is carbon. Remember, we show a covalent bond with a solid line. Now, in terms of drawing this out, okay, we're going to say that these 2 bonds are in the plane of the board. Okay, so they are on the plane of the board. I can just have them as normal lines. This bond here is coming out, and this one here is going into the board. So whenever we're showing a bond coming out of the board, we use this solid wedge over here. Okay, and whenever we have a bond going into the board, or sorry, into the paper, we use a dashed line like that. Okay, so whenever it comes to drawing a tetrahedral shape, I always start off with the central atom. I then have 2 in the plane of the board at those angles, and then I have this one coming out of the board and that one going into the board at those angles. Okay, and then I'm just going to draw my hydrogen atoms in. And that is the 3D structure for methane. Not only do you need to know the bond names, you also need to know the bond angles. So in this one, okay, the bond angle between all of them, so that just means how far the bond is from each other. For tetrahedral, the bond angle between all of them is 109.5 degrees. Okay, so with tetrahedral, this is the bond angle associated with it. So all of them have 109.5 degrees between them. Okay, right, let's now have a look at another one. So let's go to ammonia. So ammonia is NH3, and in terms of the dot and cross diagram, ammonia starts off with, nitrogen starts off with 5 electrons. It wants to gain 3. Okay, so that's a dot and cross diagram for ammonia. Now, remember, we always look at the central atom. So in this case, the central atom is nitrogen, and we count how many bond pairs and how many lone pairs it has. So remember, if the electron pair is between 2 atoms, or it's being shared between 2 atoms, it's a bond pair. So as you can see, there are 3 bond pairs in ammonia. Okay, but now we also have a lone pair. So a lone pair is one that's not being shared between 2 atoms. It's just belonging to 1 atom. So in this case, we also have 1 lone pair. Okay, now if I just grab my methane molecule. Okay, so essentially we don't have 1 bond here. So over here, imagine that we have the lone pair. Okay, and our 3 hydrogens are down here. Now, remember at the beginning I said that lone pairs repel more than bond pairs. So over here we have a lone pair, and that's going to repel the bond pairs more than if there was a bond pair over here. Okay, so because there's a lone pair, it's repelling the bond pairs even more. So what that actually does is it pushes these 3 bonds at the bottom closer to each other. Okay, so in terms of drawing the 3D structure, so we have 1 in the plane of the board, 1 going into the board, 1 coming out of the board. So it's basically the same thing as before, but we now don't have that bond at the top. We have a lone pair, so you draw the lone pair in. Okay, this shape over here, okay, so this shape over here, we call this, we call this pyramidal. Okay, so it kind of forms a pyramid shape like that. So this is called a pyramidal shape. Now, as we said, this lone pair pushes the bond pairs closer to each other. So what that does is it reduces the angle down here. So in tetrahedral, it was 109.5. It is now 107. So it's decreased the bond angle. Sorry, that's a degrees, not a 0. Draw that a bit smaller. Okay, so it's now 107 degrees. So that lone pair has reduced the bond angle by 2.5 degrees. So anytime you have a central atom with 3 bond pairs and 1 lone pair, it will adopt the pyramidal shape. Right, next one we're going to look at is, we're going to look at water now. Okay, so dot and cross diagram for water. So remember, oxygen starts off with 6, it wants to gain 2, like so. It does that by sharing with hydrogens. Now, with this one, we have, as you look at the central atom, in this case it's oxygen, we have 2 bond pairs, but now we have 2 lone pairs as well. So we have 2 bond pairs and 2 lone pairs. So what you can imagine that if we go back to our ammonia molecule, we've now replaced another one of the bond pairs with a lone pair. So we've got a lone pair here, and we have the two oxygens down here. Okay, so in terms of drawing this out, as you can see, this is a flat molecule. Okay, it's all in one plane, so it doesn't need to be in 3D. And we got our lone pairs at the top over here. Now this shape over here, it does have various names. We call it non-linear. In other books, you might see it as V-shape, you might see it as bent, but non-linear is the better name for that one. Now, because we now have another lone pair, we have two lone pairs. These two lone pairs, remember lone pairs repel more than bond pairs because we have two, they are going to repel the bond pair even more. So in our pyramidal, in our ammonia molecule, the bond angle was 107 degrees. That's now going to reduce even more in our water. This is now 104.5 degrees. Okay, so again, having another lone pair, so before we had one lone pair, now we have two lone pairs. It's now reduced the bond angle by another 2.5 degrees. Okay, and that's given rise to this non-linear shape here. So anytime you have around the central atom two bond pairs and two lone pairs, it will adopt the non-linear shape and it will have this bond angle here. Okay, right, let's now have a look at when we have double bonds. So I'm going to focus on carbon dioxide here. So in the previous video, we looked at the dot and cross diagram for that. And we saw that we had double bonds. Sorry, it's hard to draw it with a board pen, so it's coming off a little bit. And we have these over here. Okay, so that's the dot and cross diagram for carbon dioxide. Now, in this case, the central atom is carbon, and we look at the number of electron pairs around it. Now, because we have a double bond, so if you remember the structure is that because we have two electron pairs being shared over here and two electron pairs being shared over here, that gives rise to a double bond. Now, whenever we're looking at a double bond, like we have over here, we class this as one bonding region or one bonding pair. Okay, we can't really call it a bonding pair because it's two. We call it a bonding region, but it acts the same as a bonding pair. Okay, so this carbon over here has one bonding region here and it has one bonding region over here, and it doesn't have any lone pairs. So this bonding region wants to be as far away from this bonding region over here, and as you can see, the easiest way to do that is to be 180 degrees away from that one. Okay, so in this case, we don't have four bond pairs, we have two bonding regions around the carbon, and that acts as two bond pairs. So two bond pairs and zero lone pairs. So the bond pairs are technically bonding regions. And that gives rise to this shape, which is our linear shape, and the bond angle is 180. So yep, it's worth noting that if you have a double bond, that acts as one bonding pair. Right, the other shape that we have is the one that BF3 adopts. So remember, BF3 is the one where boron doesn't have 8 electrons in its outer shell once it's bonded. It only has 6. So just a quick sketch of that. Like so. So remember, you look at the central atom, in this case it's boron. Boron now has 3 bond pairs and it has 0 lone pairs. Plus 0 lone pairs. I don't have a molecular model for this, but it's going to be a flat molecule, so they're going to want to be as far away from each other as possible. So this gives rise to this flat molecule here. And we call this shape a trigonal planar shape. So planar just means it's a flat molecule. Okay, so it's a trigonal planar shape. And the bond angle, hopefully you can tell, is going to be 120 degrees. Okay, so if you have 3 bond pairs and 0 lone pairs around the central atom, that will give rise to a trigonal planar shape with a bond angle of 120. Right, and the last one we're going to look at is what SF6 adopts. So that was sulfur hexafluoride. As you remember, sulfur can expand its octet and it can have more than 8 electrons in its outer shell. So if I go to draw the dot and cross diagram of this, just bear with me because it's a little bit long. Probably should have drawn it a little bit bigger. Okay, and then the ones around fluorine. This one is tiny. Okay, so that's the dot and cross diagram of sulfur hexafluoride. Now I have a 3D diagram of this, not 3D diagram, a 3D structure of this. So we have our central sulfur, and as we can see, our sulfur has 6 bond pairs, so 1, 2, 3, 4, 5, 6 bond pairs, and 0 lone pairs. And those 6 bond pairs want to be as far away from each other as possible. Okay, so this is the shape that they adopt. As you can see, these ones in the middle here are all in one plane, and then you have one coming out the top and one coming out the bottom. Okay, so when it comes to drawing the 3D structure of this, so start off with your central sulfur. You have 2 in the plane of the board. Okay, so 2 in the plane of the board. You then have 2 going into the board and then 2 coming out of the board. So I'm just going to draw that like this. So 2 going into the board and 2 coming out. I'll just put my fluorines in. We call this shape an octahedral shape. And the reason for that is, I know it's 6, but if you were to imagine these all to be a point on a shape, the shape would be an octahedron. So that's why this is called the octahedral shape. And in terms of bond angles, so these ones here, hopefully you can see, are 90 degrees from each other. These 2 here are 180 from each other. But the bond angle that you need to write in the exam is the one that is 90 degrees. So the bond angle for octahedral, you need to write down in an exam, is octahedral, like so. Okay, so always kind of think about the central atom, how many bond pairs and how many lone pairs, and then match it to one of the structures that I have shown you. So for example, you can also do this with polyatomic ions as well. So I'm just going to do that as an example. If we have NH4+, which is our ammonium ion, okay, if I draw the structure, not the structure, the dot and cross diagram of an ammonium ion, okay, if you remember, this is a dative covalent bond, so both the electrons here have been provided by the nitrogen. The hydrogen didn't have any, so this is a dative covalent bond. If we wanted to draw that, it would be an arrow for this hydrogen here, okay, like that. If I now want to determine the structure for this, I'm just going to rub this one out. If I want to determine the structure for this, it doesn't matter that both the electrons have come from one nitrogen. It doesn't affect it being a bond pair. So it's still a bond pair. This bond pair is still technically the same as this one. So over here, around the central nitrogen, if we count the number of bond pairs and number of lone pairs, we have 4 bond pairs and 0 lone pairs. And that matches the same one that we had for methane. So if you remember, methane has 4 bond pairs and 0 lone pairs. So this will adopt the tetrahedral structure. So if I'm to draw this in 3D, it would adopt the tetrahedral structure. Don't forget the positive charge. And the bond angle here would be 109.5, like so. Okay, so if you are asked this in an exam, you are asked to determine the shape of a molecule. What you need to do is draw the dot and cross diagram, identify around the central atom the number of bond pairs and lone pairs, match it to one of the ones that I've covered in this video. In terms of explaining it in words, you do need to say, so if I were to explain in words why this shape is tetrahedral, I would say that the central nitrogen has 4 bond pairs and 0 lone pairs. Okay. In this case, because we don't have any lone pairs, you wouldn't need to say it. But if you did have lone pairs involved, you do need to make a statement that bond pairs repel more than lone pairs. And that's why it adopts that shape over here. Over here, you would just need to say that the 4 bond pairs repel each other equally, and therefore it will adopt the tetrahedral shape.